Cloud formation is a thermodynamic process, essentially a recipe for atmospheric change. To create a cloud, nature requires three essential ingredients. First, water vapor acts as the fuel. Second, rising air provides the cooling necessary to reach the dew point. Finally, microscopic aerosols, or cloud condensation nuclei, provide a surface for vapor to transition into liquid. Combined, these components allow invisible vapor to manifest as the clouds we see in the sky. As air rises, it expands and cools adiabatically. When the air mass reaches its saturation point, condensation occurs around our aerosol nuclei, forming droplets. Convection is a primary engine for cloud formation. It begins with the sun heating the Earth's surface. As the ground warms the air directly above it, this air becomes less dense and buoyant, causing it to rise. As the parcel rises, the surrounding pressure decreases, causing it to expand and cool adiabatically. Once it cools to its dew point, moisture condenses to form a visible cloud. The temperature at which this occurs is known as the lifting condensation level, marking where cloud development begins. Orographic lifting occurs when air encounters a physical barrier, like a mountain range. As the air is forced upward, it undergoes adiabatic cooling. On the windward side, cooling causes water vapor to condense, forming clouds and precipitation. This strips the air of its moisture. As the air descends the leeward side, it warms and dries out, creating a distinct rain shadow effect. This process is a primary driver of regional climate variations, creating lush windward landscapes and arid leeward environments. Frontal lifting occurs when air masses of different temperatures meet. The boundary between these masses is known as a front. Think of a front as an atmospheric collision zone. When two types of air meet, they don't always mix easily, leading to vertical displacement. In a cold front, dense, cold air acts like a wedge, plowing underneath warmer, less dense air. This forces the warm, moist air rapidly upward. Conversely, in a warm front, the warm air gently slides up and over the retreating cold air mass, producing a more gradual ascent and wider cloud bands. As the air is forced to rise, it cools adiabatically, reaching its dew point and condensing into clouds. This forced ascent is a powerful cloud-building mechanism, resulting in the extensive cloud bands associated with storms. Water vapor molecules cannot condense into liquid droplets on their own. They need a surface, known as a cloud condensation nucleus, or CCN. Common CCNs include dust, sea salt, and smoke particles. CCNs aren't just for liquid droplets. They also play a critical role in ice nucleation. Different types of aerosol particles facilitate the creation of ice crystals, which are crucial for cloud development in the freezing temperatures of the upper atmosphere. In short, these tiny particles act as the structural anchors that allow water vapor to turn into the visible clouds we see in the sky every day. The dew point is a critical threshold in meteorology. It marks the temperature at which air becomes saturated with water vapor. As air cools, its capacity to hold water vapor decreases. Even if the amount of vapor stays the same, the air eventually hits a limit. When relative humidity reaches 100%, the air is saturated. The vapor can no longer remain a gas and must transition into liquid water. This process of condensation releases energy and is the fundamental first step in forming clouds and precipitation. Clouds are categorized by their altitude. Cirrus clouds form in the highest reaches of the troposphere, where temperatures are freezing. The prefix cirro identifies these high-altitude clouds. They appear thin and wispy because at such extreme heights, they are composed primarily of ice crystals rather than liquid water droplets. Because the air is so cold above 6,000 meters, water vapor undergoes deposition, turning directly into delicate ice structures. Clouds labeled with the alto prefix reside in the middle levels of our troposphere. Spanning roughly 2 to 7 kilometers in altitude, these clouds serve as a critical transition zone in our atmosphere's stability. Altocumulus clouds appear as white or gray patches and heaps. They are primarily composed of supercooled water droplets and often signal unstable convective activity midair. Altostratus clouds present as a featureless, uniform gray-blue sheet that covers large portions of the sky. Their presence frequently precedes periods of continuous precipitation or changing weather fronts. By occupying this middle tier, alto clouds represent a vital transition point. They mark the physical boundary between the wispy, icy high-altitude layers and the dense, moisture-rich lower atmosphere. Cumulus clouds are the visual representation of vertical development. They form when localized, intense pockets of warm air rise rapidly from the surface. This rapid ascent cools the air until condensation occurs, creating the characteristic fluffy, heap-like shape that gives cumulus clouds their name. In meteorology, the term nimbus originates from the Latin word for rain cloud. When you see this suffix added to a cloud name, it indicates that the cloud is actively producing precipitation. Nimbostratus clouds are characterized by thick, gray layers that bring steady, prolonged rain. In contrast, cumulonimbus clouds are towering giants of the sky, known for generating intense, brief, and convective storm events like thunderstorms and heavy showers. The aerosol cloud paradox reveals that pollution particles act as unintended cloud seeds. By increasing the number of condensation nuclei, they change the fundamental properties of clouds. In a clean environment, water vapor forms larger, fewer droplets, resulting in faster rain and rapid cloud dissipation. However, in polluted air, more aerosols create numerous smaller droplets. This creates the paradox. Polluted clouds are often thinner and reflect less sunlight, yet they persist much longer in the atmosphere. This shift complicates climate models significantly. Recent 2026 research has shifted our understanding of high-altitude cloud formation. We now know that biological particles, such as pollen and bacteria, act as catalysts for ice crystal growth. These particles, including varied pollen shapes and bacteria, are swept into the upper atmosphere. They serve as efficient templates, allowing water vapor to freeze at higher temperatures than it would otherwise. By facilitating ice nucleation, these biological agents directly influence the properties of high-altitude cirrus clouds. These clouds play a major role in trapping or reflecting heat, impacting our global thermal balance. Understanding the life cycle of these biological ice nuclei is now a top priority for improving the accuracy of future climate models. A supercell is a unique thunderstorm characterized by a persistent, rotating updraft called a mesocyclone. It is the most organized and dangerous form of convective storm. The rotation often begins when a layer of warm air, or temperature inversion, traps cooler air below. This creates vertical wind shear, which organizes the storm's internal flow. Advanced 4D radar imaging allows us to see this rotation in real time. The Hooke echo signature is a clear indicator of a storm beginning to rotate as the mesocyclone develops. This rotating updraft eventually creates a wall cloud, a distinct, lowered cloud feature where tornadoes are most likely to originate. Wind shear determines whether the updraft stays vertical or tilts. A tilting updraft, caused by shear, prevents the rain downdraft from choking the storm, allowing it to persist for hours. Clouds function as Earth's natural thermostat. During the day, they act as mirrors. Sunlight strikes the top of the cloud and is reflected back into space. At night, the process shifts. The Earth loses heat through infrared radiation. Clouds trap this heat, acting as a blanket that warms the surface below. The net impact of clouds on global temperature depends on their type, altitude, and timing. This dual role remains a complex piece of our climate puzzle. Stratocumulus clouds act as the Earth's primary reflective shield, cooling the planet by bouncing incoming solar radiation back into space. However, a concerning hypothesis suggests that as oceans warm, increased turbulence mixes dry air into these clouds, causing them to thin and dissipate. This loss of cloud coverage creates a self-reinforcing feedback loop. Less cloud cover means less sunlight reflected, leading to higher temperatures, which further reduces cloud formation. Meteorological agencies are now developing digital twins of Earth. These are high-resolution simulations that process real-time global atmospheric data to predict the evolution of clouds. By creating a virtual replica, scientists can now move beyond simple weather forecasts. They can simulate complex microphysical properties of convective cloud systems with unprecedented precision. This technology enables the observation of subgrid processes, identifying how tiny-scale atmospheric changes influence global weather patterns. Marine cloud brightening is a proposed climate intervention technique. The goal is to increase the reflectivity of low-level marine clouds to reflect more sunlight away from the Earth. By spraying sea salt aerosols into the atmosphere, we create more cloud condensation nuclei. This leads to smaller, more numerous water droplets, which are more effective at scattering solar energy. The difference is clear. While naturally occurring clouds have larger droplets, the artificially enhanced clouds act like a brighter mirror. This process helps mitigate sea surface warming in localized regions. Specialized vessels are designed to mist seawater upward, providing the seeds for these brighter reflective clouds. This natural experiment is a focal point of current atmospheric research. While promising, scientists remain cautious as the long-term ecological impacts of such large-scale cloud modification are still being modeled. Recent breakthroughs in 2026 involve AI satellite imaging that tracks subgrid cloud processes. These tiny formations, often less than 1 kilometer in size, are crucial for accurate global climate modeling. By analyzing these subgrid dynamics, AI models have achieved a 15% improvement in short-term weather prediction accuracy. This technology allows meteorologists to transition from broad averages to high-resolution microphysical analysis. Our planet is constantly draped in a dynamic veil of water vapor and ice crystals. Statistical analysis shows that at any given moment, approximately 67% of the Earth's surface is covered by clouds. This widespread coverage makes clouds the single largest variable in predicting global climate change. Their ability to both reflect sunlight and trap heat remains the most complex challenge for atmospheric scientists. Understanding this 67% coverage is key to building accurate climate models for our future. Despite decades of research, clouds remain the primary source of uncertainty in global climate models. This is because they act as both a mirror and a blanket. Modeling these interactions requires precision that exceeds current global climate simulations. We struggle to correlate radiative forcing with climate feedback parameters. The core issue is the subgrid problem. Global models view the atmosphere in large grid cells, but the physics that form clouds happen on a tiny subkilometer scale. When a model misses these microscale dynamics, its entire projection of future temperatures becomes unstable. Until we can effectively bridge this gap between microphysical cloud behavior and global climate scales, clouds will remain the greatest uncertainty in understanding our future climate. Clouds are not just weather markers. They are the primary regulators of the Earth's energy balance. From the water cycle that drives their formation to their role in reflecting sunlight or trapping heat, they integrate our planet's complex systems. As we alter our atmosphere, we modify the microphysical processes governing cloud life cycles. Understanding these dynamic systems is the key to predicting our climate future. Clouds are truly the bridge between the Earth and the atmosphere.